That's a good subject. Yes, that's right. So, no gonna stand us. Mama was right. That's going on video. I didn't care. We had a good time just now. Y'all missed it. So we're going to talk about something new. We start the calculus on vector fields today. We do not end it. We start it. We're going to start these things called line integrals, and we're going to just beat the crap out of them like on Waterboy, all right? And then we're going to go on to how you start talking about line integrals on conservative vector fields and what that all meant, why we needed conservative vector fields and what that means, and then a whole bunch of other stuff. So let's start talking about just what a basic line integral does, what it represents, and most importantly, how you find it. I want you to think back to something. In your Calc 1 class, or this class if you've never got in Calc 1 like a lot of people, I don't really cover it even in Calc 1. This, we talked about it a while back though, in section 14.4. This, instead of representing area under a curve, which it does, it could be used to represent the mass of a straight wire from A to B. If f of x is the mass density function. Hey, now that you understand that concept. Area, we found out, was numerically equal to the mass. Area under the function is numerically equal to the mass if f of x is the mass density function. Here's the question. What if the wire's not straight anymore? Because that only worked for the straight wire, or something that's at least a function. What if it's not? Where do we start? Where do we stop? And we don't have a good answer for that. Because number one, it's not a function. Number two, it's not straight. We still would have a mass density function. So the question becomes, can we still find the mass? The answer is, well, you're nodding your head. You don't know yet, but yes. Otherwise, nope, we can't. Let's move on to the next section. Done. I get an A in this one. I wish. Class would be over. We couldn't do anything after this. The answer, yeah, like, please. No. Some classes do end here. We do not. We can do it. We can do it with a line integral. It really should be a curve integral because they're not freaking lines, all right? But they're called line integrals. Answer's yes. Unfortunately for you, you're probably thinking, but no, you want to do this, right? Green's theorem, Stokes' theorem, all this important stuff that we're going to get to, divergence theorem, surface integrals, so they all stem from this stuff. Yes, with a line integral. Here's what line integrals look like. Here's what they do. What the line integral does, it will give you the mass. It will give you the mass, but wait a second. Here's the issue, gentlemen. Here's the issue. I can't go from A to B. There is no A to B. I can't, because if I go from A to B, it's just here. That's wrong. I can't do that. So it's not from A to B. It's over some C, where C is a curve. We're going to spend a lot of time defining what C is in this class. C is the curve that we're trying to find the curve of the wire that we're trying to find the mass of. Of some function in two variables. Notice, it's not a function in one variable. We need two variables to describe it. Think parametrics, because we're about to use it. And then, it's with respect to ds. Oh man, do you remember what that meant from chapter 12 when we first started talking about vector functions? Wait a minute, this can't involve vector functions. No, we're only in vector fields. Do you remember what that was? Arc length. Now we're gonna digest all this stuff. I'm gonna show you exactly how it works in just a second. But this will give you the mass of the wire that takes the shape of this curve if what is the case? If this is what? If that's the mass density function. So if that will give the mass density at every point along the curve, that's when it works. Please make yourself a side note. I know that I shouldn't have to say it, but I'm going to say it anyway. Please make yourself a side note. I'm not going to write it down. Listen carefully. Does this thing give the curve? Yeah. Just like the function never gave the region, this function never gives the curve. This function, if you think about it, that would be a surface. Do you guys see it? Two variables, one dependent. That's a surface. This is a two-dimensional curve. We can do it in 3D. We'll talk about that later. But this is not the curve. The C is the curve, just like the R was the region. This is the function. It's a surface actually above the curve. We'll talk about all this interplays, how all this interplays right now. Right now we have two questions to answer. What's the C, and how do we deal with the DS? What's the curve? How do we define the curve? And how do we deal with the DS? You guys ready for it? Let's start. Do you understand the idea right now? What are we looking for? Mass of curved wire, where the f of xy gives the mass density function, and what gives it to us? What's this idea called? So whenever you do a line integral, you're basically just finding mass of a curved wire, where f of xy is the mass density function. Show of hands if you feel okay with that. Let's start with the C. Well, since we're not dealing with a function, but rather just a curve on a plane curve. Well, we've done that before in Calc 2 in section, well, for us it was like 10.2 and 3. We dealt with that with, how would you define a curve that's not a function? I see blank looks. I don't know. Am I scaring you? You do it with parametrics, because that will tell you a point at every xy, and you go around it at a given time. So we introduce this new variable t for time, or whatever you call t, it's just a parameter. But let's use some parametrics. So for C, we're going to use parametrics. Okay. And DS, you guys already told me what DS is. What's the DS part of it? What's that deal with? Arc length. Yeah, with respect to arc length. So this just has this arc length idea. Now let's get into this. Here's how this basically works. Honestly, I don't even care if you write it down. I'm going to give you the formula here in about 20 minutes. But I want you to see where, I could give you the formula, we just do the math. That's a bunch of crap. You need to see where this comes from and actually understand why this does what it does. The whole concept was the area under a curve can also numerically represent mass if we have a mass density function. Do you guys get that? We've done a lot of it in 14.4. We're doing the same thing, but here's the idea. F of xy, what is it? If you graphed it, what would it be? Surface. It's a surface. F of xy, a surface. Will give you a height above every point on that curve. Look, here's my curve. Here's the z-axis. Here's a surface, which also represents mass density function. Here's your curve, here's your surface. That surface will give you a height over every single point along that curve. Do you guys get that idea? Got a little too excited. Well, DS stands for arc length. In fact, DS stands for the differential with respect to arc length. A real little teeny piece of the curve is what that DS stands for. The length of and when I say real teeny, I mean, differential sort of teeny, like close to zero sort of teeny. DS gives us a little teeny length of the curve. I can spell little. Man, now that I misspelled it, it looks funny. Is that how you spell little?
Yeah.
That is, right? Do you ever misspell something that looks funny, then you spell it right, and you go, no,
Yeah.
and then it's, oh crap. It happens to me all the time. That's why I teach math. All right. Gives a real little length of the curve. When I say real little, I mean real little. Okay, well, wait. If ds gives length, and f of xy gives height, we have the length of the little part of the curve. Little part means like just this teeny, right at the point, teeny tiny. We have the height above this specific, look! What's this give you? Height above the point. What's this give you? A length. What's height times length? Area. This is area. This is area of each little teeny segment along that curve. Because it's taking this, it's saying, here's a little teeny part, here's the height, there's a little area. Little teeny part, here's the height, here's more area. It's a calculus idea, you know that idea. Then we add up all of these. So this gives us area for each little teeny piece. Height times length equals area. You go, okay, that's fantastic. But that's only one of them. How do you find all of them? You add them. You add them with an infinite sum. That's an integral. So the integral adds up all the height times area, height times length, adds them all up, we get total area. So this is a little area for each little teeny piece. This is the total area for, well, here's what happens. Here's the idea. I need you to get the idea. Here's what a line integral does. It says, what I want you to do, take this curve. Take the curve, project the image onto some surface which represents, are you listening right now? Take the curve, project the curve, 2D idea, onto the surface. It's going to create a curve on the surface. Between that curve on the surface and this curve here, there will be a whole bunch of differing heights. Take that integral along that curve. It adds up all the little areas. It's going to give you the area under the curve on the surface, but only above this particular curve. It's giving us an area concept. That area is numerically equal to mass. That's line integrals. That's how it works. If you're like, well, wait, okay. So this adds up all the areas, giving us the area under f of xy, but only over the path c. Did you guys catch that from what I just explained? I'm going to write that down so you don't lose it. So what this does, adds up the areas, and it gives the area under the function, but only over the path C, only over the curve C. Only over the curve, the path, however you want to think about it, C. Wait a minute though. Wait a minute. Surfaces get volume, dude. You can't do that. How can you just go over a path? You can't even do, can you, wait a minute, can you do that? Well, let's think. What would, I'll do it here. What would that give you? That's a volume idea. If I take a volume idea, which integrates across two directions, and I subtract or get rid of or remove one of those dimensions, let's take volume, and let's say, well, wait a minute. Let's keep the same function, but instead of integrating in two, let's just integrate with respect to one direction. Same function, but only along that curve, the arc length along that curve of still the surface, but I'm not integrating across the whole region. There is no region. There's just the curve. A volume idea, say take away a dimension, you ain't got volume anymore. You got area. That's practically what we're doing. I'm going to give you 2 drawings of this just so you totally get the idea. Here's what's happening. If this is C and this is our surface up here, we're basically creating a pathway on the surface that's right above the C, and we're finding the area, and it's curving around, okay? So we're finding the area between those 2 curves, essentially, and it's curving on the plane. If you want a better picture, here's the better picture. Now listen, a lot of people have this confused in life. Well, not a lot, because not a lot of people make it this far in life. I mean Calculus 3. It is life. If I take this, my C, the curve, it's not on the surface. It's on a plane. It's on XY. It is on a plane, unless you're talking about space curves, and that's when we're dealing with it's a little bit later in this section, okay? But right now, your curve is on a plane. Verify that you understand that. What happens is this shoots up to the function. Man, shoots up sounds bad. Don't do that either. Okay, that's bad. It projects onto. So imagine this curve projected onto the surface. What's going to happen is this is going to create some sort of curve on the surface. Can you guys see the projection I'm trying to draw for you? Yes or no? I need to know. Are you sure? This is not your C. This is a projected image of your C, your curve, onto the surface. Then what we're doing is we're finding the area. They should match each other. It's like a, kind of think of a plane. Normally we just take this plane and we go, sorry, not that one. Take this plane and we go, now imagine if the plane was curved. You'd still get that. You'd still get an image. It's just going to be a weirder image. It's going to be this curve. And then we're finding the area between the top curve and the bottom curve. And they're directly right over each other. If you look down, you'd see one curve. That's the thing. We're just finding the area between this curve that is the projected image of C, which is on the plane. So fans understand that concept. It's a weird concept. That is how line integrals work. A lot of people say, oh, that's your C. That's not your C. That's not your C. That's the image that C creates on the surface when you project it upwards along parallel to the Z-axis at point to point, and then find the area between them. So we think of C as a curve. Well, think of C as projecting a curve onto the surface. Then we find the area between that curve and the XY plane, and that area is numerically equal to the mass if that thing is a mass density function. Bam. With me? You sure? Now we get the fun stuff. This is horribly hard to deal with because we'd have to define all our curves in terms of arc length. That sucks. I don't want to do that. Bless you. And the curve would be difficult to define. So we're gonna actually use parametrics to our advantage to make our life actually easier. Are there any questions on this before we do that? Yes.
So to do this, would that be impossible if that curve wasn't a function, like the one you just erased? Wasn't?
This one?
Is that if you're doing the single
this
over
one?
a curve? Yeah.
This one?
That one.
This
if that
one.
wasn't a function, that wouldn't be
This?
possible, then, right? Yeah.
That?
Yeah.
Or that? The C or the F?
The C.
Both. This has to be differentiable continuous over the curve. This one also has to be at least connected. If it's disconnected, then we have to just do 2 integrals. Also, if it has a sharp point, that should sound familiar. We have to do 2 integrals to do it. Does that make sense?
Yeah.
Okay, so back to, yeah, good question. Thanks for that one. Back to it. So this thing is going to find the area under f of x only along the path C, not a region, just over a curve. That's why it's area, not volume. Here's our goal. We want to change an integral with two variables into an integral with one variables. How we do that is with parametric equations. So let's start. Let's start with this. What if we were able to define both x and y as some parameter? Hence the name parametric equations. Have we done that before? Oh yeah, lots of times. It's called vector functions. That's literally what we had. So now, what about ds? Well, if you think about arc length, it's a Pythagorean theorem idea. In fact, you literally have this in your calculus. I think it's Calc 2. In your Calc 2 notes from like our chapter 10, you will have this back there. Looks like this. It looks nasty. Do you remember that at all? We talked about it in this class. We talked about it in Calc 2. I'm going to show you once and for all again, because I've already shown you a little bit of it. You check this out. We're going to have a gestalt moment here in a second. The only way we get to do this is by redefining some stuff. We got to use parametrics somehow. Let's redefine this. And we know that we can redefine any curve, like ever, if we do x sub t I plus y sub t j. This is the basis for our understanding of how vector functions work and how this stuff is going to work. Are you guys okay with that? Now check this out. Stick with me. If we take a derivative of this, we get x prime t I plus y prime t j. You with me still? Can you explain to me how you find the magnitude of a vector function? How do you find magnitude of any vector like ever? Explain it one more time. How do you do it? Square root. Adam? Square root. So the magnitude of this, we've already done it, would be square them. Square the components, we mean. Square them. Add them. Square root them. What? No, that can't. It's freaking crazy, right? Do you see it? Do you see it? I'm not going to draw it in crayon for you guys. You guys see it. Hey, what? That's... So wait. We can replace the ds with this. Magnitude of the vector derivative of the vector function dt. We can always replace it. If we can redefine by parametric with our vector function, which we're going to do anyway, then we kind of get a twofer. We get a double up. That's awesome. That's fantastic. So this this changes for us. It's a nice change. What it changes to is still an integral, but it's no longer over the c, because if we redefine c as this, we say let's redefine that thing. Let's redefine that as our curve. Listen carefully, please. Look at the board. Some of you guys aren't watching. If we redefine that as the curve itself, not the function, but the curve, then this stands for the arc length of that curve at any point. That's what we want. So this right here becomes our curve. That means in order to travel along a curve, I don't have to go just along the arbitrary c. I go from a to b, where t is now my parameter. T is now my variable. So this says t equals a to t equals b. That's fantastic. My function changes. It now gets reparameterized in terms of t. I don't have a ds anymore. ds now changes. That's crazy. That's fantastic. In fact, here's the craziest thing. Here's the craziest thing. I'm going to hopefully make it all just be solidified right now for you. You need to think back to chapter 12, though. If you remember from chapter 12, we did arc length. And we said the arc length was this magnitude of this dt. Does anybody recall that? Yes or no?
Yes.
The length of a plane curve. The length of a curve in space. The length of, which is how we get to take this and go 3D with it, okay? The length of the curve was this. Take the derivative of the vector function, take the magnitude of it, integrate it. It took us a whole long time to do it, and then go from A to B. Head nod that you're with me on that one. Now look, if we want to go from length to area, length times what gives us area? If this is length, then area would be length there's length from t equals A to B. This is just length. But wait a second. What's the height? What gives us height above the curve? What gives us height above that? The function. Length times height equals area. Length times height equals area, which equals mass. That's where this is coming from. I've shown you like 4 different ways now. This all hopefully should make sense to you. Do you guys see where that's coming from? This was arc length originally. This is just length of a curve. That's all we're doing. Now we're just putting a height aspect to it above the curve at every single value of t. And then we're adding up all the little areas. We show it this way, this way. We've already talked about the volume area idea. Now we're talking about arc length idea with a height component. And I've proven this to you through just some use of parametrics. This is where we live. That's a mass of that wire that's shaped like a curve. If this is a mass density function, this is what we're going to be doing. Crazy? That's a line integral. Now we're going to take this and run with it. Here's what's going to happen for our future here. We're going to talk about just basic old line integrals. Then we're going to start talking about these are not in vector fields right now, okay? You haven't learned about line integrals, so I got to tell you. So we're going to take line integrals now, and then at the end of the section, we're going to start putting line integrals through vector fields. So we're going to combine these two ideas. Some interesting things are going to start happening. Some of you physicsy people are going to start saying, oh, that makes sense, because I've learned this in my physics class, you just didn't know the calculus way to do it. You're going to start learning about that right now. So we're going to start some examples. Get through as many as we possibly can. We'll probably just do one right now, take a break, and then come back and hit up as many as we can. Or do you want to take a break now? Would that be helpful? Let's do it now. Let's go. Okay, as promised, some examples. I will be honest with you. These line integrals go from very easy to very hard and everything in between. They can be extremely easy. This will be an extremely easy one. You just need to know how to do it, okay? There will be some where they are not so easy, and I'll show you why they're not easy and how to deal with it. So, number 1, line integrals. What do they find?
Area.
The area, but we think of it as mass of the wire that's not straight anymore. It's a curve. It's on a plane, but it's the mass of that wire if that is the mass density function. Head nod if you're okay with that one. Now, here's our goal. Our goal is that you're going to want to change this to what we just found just a little while earlier. An integral from A to B, where we've redefined x and y as functions of t, a magnitude of the derivative of our vector function dt. You go, man, that looks like a lot of crazy stuff. It's not. It's actually all given to you. So I'm going to show you that right now. This right here is the number 1 thing that you want to be given to you all the time. If it's not, our work becomes a lot harder. So if I give you integral, I give you curve, and I even give you bounds of integration, you're practically done. I want to show you exactly how to do it, though. Here's where you need to start. Number 1 thing. Look. Number 1 thing. Freaking pay attention. Goodness. Number 1 thing that you do before you start anything else, if you're given a vector function, literally identify what x is, what y is, and if possible, if you have a z, what z is. So can you tell me, right setters, what is x here?
QT.
Perfect. Do you remember that? That x is the x component. Do you remember that? No?
Yes.
Okay. Well, if you didn't, you probably just learned it right now. So you tell me what y is, and what's the y? What's the y? This is why this is easy. It's automatically reparameterized the curve for you. What that means is that every time you see a y, you just replace it with that. Every time you see an x, you just replace it with that. That's it. That's pretty much all there is to it. Also, notice something. These are in terms of t. You have bounds of integration given to you right there, from 0 to 1. We're practically done. So number one, if you're given a vector function, identify x and y, do that first. Before doing anything else, do that first. Next step, after you do this, start with this. Take the derivative of whatever the vector function is. It will still be a vector. Follow? Derivatives of vector functions are still vector functions. There's derivatives of them, they're tangent. Tell me quickly, come on, we're just going fast with this. What is it?
2y plus 3t squared j.
Perfect. Start with that. So label x, label y, find your derivative. Again, remember the goal. Look at the goal. The goal is look at what this says math-wise in English, okay? What this says is replace your x's and y's with their components. Find the derivative. Done. What do those vertical lines mean? Find the magnitude right now. Magnitude means that we square, we add, and we square root. So here we get that. 4 plus 9 t to the fourth. Show of hands if you feel okay getting down that far. Notice how we're starting to use a lot of the old stuff that we've had. Now you make your substitutions. So we start with what x and y are from whatever your curve is. That's important. You got to get your x and y from your curve. Then we go, okay, well, what are we trying to do? We're trying to reparameterize. Done. We're trying to find the derivative of the vector function. Done. Then we have to find the magnitude. Square them, add them, square root them. Done. Can you see how this can get very difficult for you? When you start finding magnitudes of derivatives of vector functions, they can get nasty. All right, well, let's start making our substitutions now. Can you please tell me real quick, what's our bounds of integration? Since we're all now in terms of t, dt, that has to be t, and the t is given to you. What's the bounds of integration?
0.
This is your function reparameterized. Just take your variables, plug in the freaking parameters, okay? So what variable do I have?
Y.
Y is here. I just replace it. So this should be what?
TQ.
Then ds is this piece. I proved it. Just before our break, I proved it. This is this. Just replace it. So what's the next thing?
Square root of 4 plus 9t to the fourth.
Yeah, perfect. One more thing.
dt.
Hey, how many integrals do you have?
1.
It's all got to be one variable. That's why we had to switch it. Because if we have x's and y's, you can't do a single integral with two variables. It doesn't work. That's why it necessitated the reparameterization into t. Now we have, hey, look, t matches up. It looks great. It's Calc 1. It's really Calc 1. Can you guys do that integral? How would you do that integral? U sub, some other stuff. If this is the mass density function of that curve, then the area under that surface, only over that curve, is equal to the mass. What this is, I'm not going to do any of these for you. This is literally Calc 1, okay? You can do U subs and change bounds. This right here, your answer ends up being 1/54th, and it's nasty too, 13 root 13 minus 8. Yeah, what is that? What's that stand for?
Mass of the y.
Mass of the y. If that's mass density function, then that's the mass of the wire. That's it. That's all we're doing. Should fans feel okay with it, for real. Is it easy, medium, or hard? It's all set up. All set up. All about that. Now, it is straightforward. It can get unstraightforward real quick. Okay, get all functioned up real fast. All right. So we're going to start dealing with some that aren't that easy, like this one. What happens if I don't give you the vector function? Then you have to work for it. So you got to find it yourself. You make your own parametric equation. I'm going to show you how to deal with it. So let's say we got this integral. We go, okay, fantastic. What's going to happen is I'm going to have to redefine. I'm going to reparameterize x and y. That has to happen. We change two variables into one variable so that we can do a single integral with it. Okay, well, what's our curve? Curve is the right half circle, x squared plus y squared equals 9. Head nod if you're okay with that one. If you want, you can draw a picture. You certainly do not have to. But this is a right half circle. What's the radius of the circle? That's the curve. Now, before you guys get crazy, are these double integrals? Then you can't have a region. You have a curve. This is not polar. It can't be because it's not a region. Your r does not go from 0 to 3. Your theta does not go from negative pi over 2 to pi over 2. That still happens, but only because we're on the curve from that length. We're not talking about a region here anymore. We're talking about a line. We're talking about just this line. And don't you understand that? That's a big deal. So we're going to have to switch our thought process a little bit. For circles, when you get them, use your normal reparameterization, where you go, well, hey, what's x equal to change for parametric versions of circles? X equals what? And y equals? Now, we can get even more specific. What is our r? How much is it? 3. It is a radius of 3, right? So, I mean, if x equals 3 cosine theta and r equals 3 sine theta, it's going to go right along this circle. So for circles, use that, and then even get more specific. So, we can do that. That's fine. They go, well, how's that fine, man? We had a vector function, and we don't have that. We don't have that now. Stop, look, so I don't lose you right here. You can't miss this. Check it out. From the vector function, we were able to glean x and y, correct? So if I give you x and y, can you go backwards and create a vector function from that?
Yeah.
Then do it here. You have everything in terms of, oh shoot, well, there's only one thing. Theta's great, and you can stick with theta, but typically instead of theta, we use what variable? Let's just change them to t. That way we stick with our parameters.
So theta equals t?
Yeah, you could do that, or just call them all t. But understand, when you do it, the reason why I put the theta first, you understand that's still an angle, all right? It's still the angular measurement of this. We still have to have it. It's just we call it t most of the time, so all our formulas work out real nice. It's our typical parameter we use. You guys follow what I'm talking about? So if we're able to get x and y from a vector function, we can get a vector function from x and y. Let's write it. Remember that vector functions are the xi plus the yj. Do we have an x?
Yep, yes.
What is it?
3 goes in.
We got a y. Let's just plug it in. Okay, so first thing, we were supposed, look how the steps always work for you. I always try to give you stuff that's universal. Look how the steps work. Here, the first thing we did was find x and y. Here, the first thing we did was find x and y. That's the first thing. The next thing we did was take a derivative of your vector function. Well, we had to create one, but what's the next thing you're going to do? Remember, we're always trying to build this. We've already done this. We've already redefined x and y. That's fantastic. Right now we need to find the magnitude of the derivative of our vector function. That's why we had to build a vector function. Without the vector function, how you can take a derivative of the vector function? You with me? So get your x and y from your vector function, or use your x and y to build a vector function. But either way, you have to have one for this to work. Understand that concept? Yes or no?
Yes.
You have to have. So take your derivative. That's step number 1 after you find your x and y. We're going to go quickly here. So can you please tell me what this becomes?
-3 sine t.
Plus or minus?
Plus.
3 cosine.
Perfect. What's the next thing you do?
Take magnitude.
Let's take the magnitude. So step 1, derivative. Step 2, magnitude of the thing that you just found. How we do it? Well, it's same thing. You find magnitude for anything. Square them, add them, square root them. Can you please tell me what, and this is so nice, I love circles, because when you take the magnitude of the vectors that create, the circle, then it's always the same. It's always got to be the radius. Probably didn't even have to do any of this work. What's the length of the vectors that's touching the circle? 3. Hey, how about that? Love it. Love getting the 3. Do you see where the 3's coming from? Can you please right now, and I'm begging you, please don't make up your own math. If these ain't regions, you can't put an R there. Don't put an R squared there. It's not R. They got to be T's. Don't put a T squared there. It ain't going to be that either, okay? You take and you substitute these for your X and Y. That's what you have to do. Can you please try that? So our integral's got to change. Inside that integral, we have x squared. Tell me right now what the x squared is going to change to, please.
9 cosine squared t.
That is x squared. So we have x, here's x. Square it, we get 9 cosine squared t. Plus 9 sine squared t. Show of hands if you're okay with that one. Okay, well, we're on a roll. That right there is just reparameterizing the function. That's exactly why we had to do this. And why we had to do this was to get the second piece. Now we just got to tack on what? 3. 3 what? Let's take a moment. Sometimes you do math so fast your brains can't absorb it. Let's take about 10 seconds. I want to make sure that you see where everything's coming from so far. We've left out a major piece. We'll talk about the major piece in a second. But so far, are you okay with using that for circles? Not R squared, using this for circles. Taking these things, radius of 3, and using them to reparameterize your function. Head nod that you're okay with that one. You don't just lose this, you use this. Then the ds is literally the magnitude of the derivative of your vector function, dt. All those pieces have to go there. Show of hands if you're okay with all those pieces. Now, lastly, what are we missing? If this is why I did the theta at first, so you guys see it. If this t is really the angle that's taking us along this circle, where's the angle start? It is the angle. I use theta so you see it. Negative pi over 2 all the way to pi over 2. Yes. Yes. And now if you're okay with that one. How about this one? What if it didn't say the right half circle? What if it said the upper half circle? If it was the upper half circle, it would go from where to where? Beautiful. That's fantastic. Now, this one is going to be a real nice integral. What are you going to get?
19.
You're going to get 9 times 3. Don't forget that one. Don't forget the 3. This whole thing right here is 9. You factor the 9, you get sine squared cosine squared. That's 1 times 3. That's 27. So this gives you That gives you that. That's it. Do a very basic integral. Your variable becomes t. You plug in pi over 2, subtract another pi over 2. That's basically adding that together. You're going to get pi. Here you get 27 pi. We're well past the spend an hour working out integrals part. We're very much to the, hey, how do you set this junk up so we're set up for success part. That's where we're at right now. Do you feel like you're getting set up for success? I don't want to leave you hanging at all. That's not the point of Calculus 3, is to blow by you with this crazy stuff. Just to make sure that you actually understand the crazy stuff. Do you feel like you understand the crazy stuff?
Yes.
Not too much, though. It'll make you crazy. Okay, let's continue. We got probably, I'm going to try to do 2-3 more examples, and I'm going to leave you right before we talk about line integrals over vector functions, vector fields, sorry. Let's look at the line integral of 2xy ds over the curve, where the curve is, well, it's a segment. It's a segment from -2, -1 to 1, 3. And you go, okay, well, does this qualify as an easy one or a hard one? It's not an easy one. It's not an easy one because I don't specifically give you what. What do you always want to have when I give you these things? What do you want to be there? You want the vector function because you have to take the derivative of that. Have I given that to you? No. I also haven't given you any x's, any y's, or a way to transform that. That's a nastier type of problem. I'm going to show you what to do with this. Make a huge note. Make a huge note right now. To create parametric equations for segments, which is what we have, you always want your t to go from 0 to 1. Always. So for segments, always, even in 3D, from 0 to 1. T equals 0 to 1. We want that. So we're going to force it to happen. All of these things for segments are going to look like this. It's not magic. It's not a coincidence. All of your segments are going to look like this. And if you had a z, it would be C3 plus PO. C3PO? No, okay. That's not C3 plus K3T. I had to throw a Star Wars one in there somewhere. Why? Does that look familiar to anybody in there? Those are lines. Segment is part of a line between two values of t. What values of t? Those ones. So because we can reparameterize with any variable that we want, we choose t, we say, hey, let's just make it so that t starts at 0, ends at 1, and make sure that we fit that, because that's how we define a line parametrically. That's it. Now how do you do it? Call one of these things the point at t equals 0, and call one of them the point at t equals 1. Please listen very carefully to my words right now, because I don't want you to miss this. It doesn't matter if you are defined as arc length, which order you do. It does matter if you're not defining arc length, which order you do. Absolutely does matter. So here, it doesn't matter. You're defining arc length, pick t equals 0 to be this one or this one. Does not matter, it's going to work out exactly the same. The opposite is not true if you don't have a ds there. Now, are there cases when we don't have a ds? Absolutely. We talk about this in just a little while, okay? So I'm going to talk about it later, but I wanted to give you the kind of, to preload this information. Does that make sense? So let's call one of these t equals 0. Which one do you want to call t equals 0? What do you think? Sure, that's fine. So set these points so that this happens. So that when t equals 0, you're at that first point, and when t equals 1, you're at that second point. That's going to help us a lot. And now that you're okay with that. So, well, let's start. If I let t equals 0, then I'm at this point right now. Listen carefully, listen. If I'm at this point right now, what's my x value at that point? -2. What's my t value at that point? So let's try this again. What's my x value? What's my t value? What's my x value? What's my t value? Use it. It will automatically solve for your C1, always. Did you see how to do that? Sorry. No? Some of you guys weren't even focused. You're like, listen, if this don't make sense, the rest of it ain't going to make sense.
Yeah, okay, that makes sense.
This makes sense. So you go,
K times t.
at t equals 0, your x is -2. So use it. At t equals 0, your x is -2. Do you see how this is always going to give you the starting x value for your C1 no matter what? It's going to happen. Now we go, okay, well, this is not enough because right now this gave us x equals -2 plus k1t. That's not enough. We need to solve for the k, but can I do it? Yes, because now I have another value of t to use. Does that make sense? Hey, at t equals 1, what's the x value? At t equals 1, the x value is 1. The t value is 1. That's what's happening there. Do you guys see it? And then we can solve for the k. Okay, well, if I add 2, how much is the k? Which it means that at t equals 0, I get, well, combining these ideas, I get x equals -2 plus 3t. I solve for C1. I also solve for k. It's going to take you both points to do it. Now, I know this, even though it's just some basic algebra, some people get really jacked up on this. Can you please try it with the y? Give you about 30 seconds. Do not just wait for me. That's a really bad way to learn anything in life. Is just waiting to watch somebody. You need to take this right now, set up your at t equals 0, use it y here with a t equals 0 and find my C2. If it's not -1, you're doing something wrong. Then use that point to figure out your k. Please try that right now. By the way, I'm not lying to you when I tell you the setup is the hardest part of calculus. It's all about the setup. Integral's pretty easy at this point. Most time. Hey, for t equals 0, did you try it? Did you at least try it? I don't care if you're making mistakes on it right now. You're still learning it. I need you to try it. Put something on your freaking paper, okay? Try to locate what the y values are for t equals 0 and for t equals 1. What is the y value for t equals 0? So when I have t equals 0, my y value is... You need to be answering me right now. When t equals 0, the y value is... When t equals 0, the y value is -1. That's all we're doing. You're just finding your c. So if you start here, you go, hey, at t equals 0, my y value is -1. My C2 value, I don't know. My K2 value, I don't know. But my T value, I do know. It's 0. It eliminates this whole thing. And now we know that C2 is negative 1. See to it that you know how to do it. Always take advice that rhymes. Do it all the time. Okay. We can do this all day. Play in the hay, make things out of clay. I digress. It's been a long day. What do you say? So we get. Are we done? No, we're not done. We're not done. We have this now. You just solved for this. Y equals negative 1 plus K2T. You've used one point to get the C. Now use the other point to get the K. Hey, what's the Y value at T equals 1? 3 is the Y value when the T value is 1. Are you starting to see why we use 0 and 1 for T all the time? Because you can do any numbers you want. 0 and 1 are the nicest for segments. Okay, well, hey, you know what? Just add that, and K2 is 4. So Y becomes look at it! Doesn't it look like part of a line to you? It is a line. That's all we're doing. And we're making a really easy line. Should fans feel all right with that one? Okay, now, we have our X. We have our Y. That's the first thing you always do. I'm not lying. That's the first thing. What's the next thing that you would do? Remember over here, we found our X, we found our Y. What was the next thing? No, because we don't have something to take a magnitude of right now. What's the next thing we do when we have an X and a Y? If you're not given this thing, which you're not, you have to find this thing. What is it? You have to find your vector function. Vector functions are very easy. X component I, Y component J. Hey, do you have something that's equal to X and Y? Can you please make for me the vector function right now? We're going to do it up here. So as soon as we solve that, well, okay, well, this I, that's our X. Don't be fancy with your signs, just put them in parentheses. This J, I'm going to stop right now. If we would have had a Z component, you would just tack on that Z component right there. It's done exactly the same way. Also, I'm going to give you guys a shortcut right now. Whenever you have segments, are you listening? It's going to save you time. Whenever you have segments at your T equals 0 point, you saw the math on it, these will always become your C values. Sorry, these will always become, your C values. Right there. This is your X C value, that's your Y C value. X C value, Y C value. It has to happen that way because you're setting T equal to 0. It has to happen. Does that make sense?
So same as T, whatever T equals 0 will be.
Set T equals 0, man, you're going to get these numbers again, and that's going to be your C values. We'll see some of that later. We're going to do one 3D in a minute. Question?
Never mind. Answered it.
Thought so. Oh, yeah. What now?
Magnitude.
This was 1. Finding that. Oh, yeah, well, that was actually, you have to have that no matter what. So that's not 1. That's a necessity. 1 is once you have that, you use it to find your X or Y. Well, we already did this. We're kind of going backwards now. We found our X and Y first to make our vector function. Now we take a derivative of said vector function, and you get what, please? Come on, quickly. What do you get?
3i plus 4j.
Hey, that's pretty darn nice. What's the next thing that you do?
Magnitude.
Magnitude says you square them, add them, square root them. 3, 4, 3, 4, 5, 20, 3, 4, 5, triangle. So magnitude of the derivative of the vector function says square them, add them, square root them. Do an important step right now. I need you to translate this into something that's actually doable for you. Can you please do that? Use what the x is, reparameterized. Use what the y is, reparameterized. Use what the ds is, reparameterized. Set it up, don't start it, just set it up. Did you try it? It shouldn't take you too long. Did you try it? Did you put something down? What goes right here? Where'd you get that? Hey, it says reparameterize that. We got a 2. We got a 2. We got an x. No, we can't have an x. It's all dt. That's why we reparameterized this. So that would be -2 plus 3t. Is it starting to sink in? What's the next thing it should have right there? Perfect. You know, just like the Jacobian we learned about in 14.8, do you understand with constants, it's very, very easy to forget this piece right here? Your magnitude, it's got to go there. What goes there? Oh, crap. What about my bounds of integration? What are those? That's why we choose them, because they're nice. Choose any numbers you want. 0 and 1 work the best. That's why we pick them for segments. Integral. Easy, medium, hard. What do you think?
Easy.
Distribute. Combine some like terms. Basic integral. I'm pretty sure y'all can do it. This ends up being 5. If that's the mass density over that segment, that has a mass of 5. Yeah, feeling good about it or not?
Yeah.
Let's just try one more. Let's see if you learned anything from this. I want to tell you, I'm not going to write any special notes about it because it's the same idea. We know that vector functions from 2D to 3D is a really easy transition. You just add a component. That means it's a really easy transition for these as well, which means that we can find not just mass of curves on planes, a plane curve, parametric, but space curves. So a mass of a wire that's traveling through space. We can do, it's the same exact thing. We just extrapolate one dimension higher. So let's change this problem a little bit, and I want to see if you can do the parameterization of x, y, and z by yourself. I want to see if you can do that. It's not hard with what we're given. Use the shortcut that I talked about. Okay, if we put this together, we know that we're talking about line integrals. The first thing you need to do with line integrals, no matter what, is somehow get what? That was a lot of buildup for no punchline. Oh my gosh, that was sad. It made me sad. My heart hurts just a little bit for you. I'm going to have to eat my pain later. So, look. Don't make me eat my pain. You answered the question. What's the first thing you need to do this? Keep in mind that everything you need's got to be t's to the end. What's the first thing that we've done every single time? What's the first thing? Before the vector function, even. Before the bounds, even.
Defining x.
X, y, z. You need to find x, y, and z. That is your number one thing. Because you'll get it from the vector function, or it will allow you to create the vector function. But either way, you have to have it. Can you please do that right now? This is a segment. I told you what to do for segments. I want you to start defining the parametric equations for that line in 3 space. It's going to look like a parametric line because it is. What are the values of t you should use? Come on, what are the values of t?
0, 1, 0.
Which one would you call the t equals 0? Does it matter if we have that?
No.
Does it matter if we don't have that?
Yes.
Which one's the t equals 0? If you're confused about it, always put the first point. then this one's going to be t equals 1 because we always want our bounds to go from 0 to 1. For segments, we always want that. For other types of curves, we don't get that, but for segments, we want that. Did you catch the shortcut from the first one? The shortcut says this. If you're like, man, I don't know what you're talking about. If you plug in t equals 0, your c values for x, y, and z respectively are going to be these three numbers. Which, oh shoot. Whoops. Why not? Not y, z. So if I plug in t equals 0, we are going to get 1, 1, and 0 as those c values. You guys understand that's a nice shortcut to make. That's a good thing. Plus, the other ones I'm not so sure. But that's why we have another point. And an easy, yeah, I did twice. And an easy number to plug in. So t equals 0 gives us this. Try the rest of it. Plug in t equals 1, plug in the values for t equals 1, and figure out what your k is, and then you're done. Then you have automatically reparameterized that. And that's the hardest part, really, in the setup, is just finding the parameterization. Ladies and gentlemen, can you please tell me at t equals 1, what is the x coordinate of the point at t equals 1? 2. And since we're always using 1, it just gives us k. It just gives us whatever this number is plus k times 1. It's just going to be k because we always use 0. We always use 1. You're starting to see the pattern here. Starting to see the thought process. Ladies and gentlemen, yeah or no? Okay. This next one, can you please tell me what the y value is at t equals 1, please? Y value at t equals 1 is 3 equals 1 plus k. Are you following where the 3 equals 1 plus k is coming from? Last one. What's the z value at t equals 1? Z equals 1. Yeah, plug it in. Z equals 1. T equals 1, plug it in. T equals 1. You end up getting this. You end up getting this, and then you solve for your k's. Head nod if you're okay with that. So let's do that. Our k, therefore, is 1, 2, and 1. Just 1, 2, and 1. Can you now write down what your x, your y, and your z are? Right-siders, I want you to do it for me. Tell me now what my reparameterization is going to be. What's the parametric equation that lets me redefine that segment? Please tell me explicitly, quickly.
X equals 1 plus t.
Somebody else, can you tell me?
Y equals 1 plus 2t.
And lastly, somebody else.
0 is t.
Z equals just t. That's it. If you can do that, man, you're halfway there. Like literally. Questions or comments? Are you getting stuff out of it?
Yeah. Since it's 2 points and we're making an equation of a line, couldn't we find the vector between those 2 points and then use the initial point to just go straight to the equation of the line? So basically,
It's basically what we're doing.
Okay, yeah.
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 Same thing. You're starting at your initial point. Yeah, pretty much. You're finding the vector between. That's what you're plugging in the point for. It's exactly the same thing. Do it however you want. I don't care. But somehow get your parametric equation back. That's what I'm looking for. Now, come on. Let's go quickly on this stuff. We're just about set up. What's the next thing we do once we find our x, our y, and our z? Everybody, come on. What do we do? So do it. Make your vector function. Everything hinges on your ability to make this vector function or get it somewhere and get 2 things. Your x, your y, and your z, and your vector function. If you have those things, you're good to go. If not, then you're having some troubles. So the way vector functions work are we take our x component I, our y component, j, and our z component, k. Since you've already determined those things, this is pretty nice. We have 1 plus ti, we have 1 plus 2tj, and we got t, k. Did you guys get that for your... Now, true or false? I should take a derivative of that right now, or I should find the magnitude of that right now.
Derivative.
That was not a true or false question, my bad. That was a horrible question. It's been a long day. Take a derivative. Once you find your vector function, you automatically either have x, y, z given to you, or you've already determined what that is. So now you're on the home stretch. Take a derivative of that vector function before you take the magnitude. You have to do that. So here, this one's kind of nice. What do we get, please? Plus just k. Can you find, what's the next thing?
Magnitude.
Let's find the magnitude. Magnitude, even with three-dimensional vectors, still is square them, add them, square root them. Hopefully, you got the square root of 6. Did you get the square root of 6?
Yes.
Okay, for the last step, I want you to translate this integral, this line integral, into something we can actually do with a t variable. Where do we start?
Oh, 0.
What has to go in here?
The redefined.
You see that if you can't do this, you can't do that. This is your reparameterization. It does two things for you. It builds a vector function from which you get, well, I didn't write it, but from which you get the magnitude of the derivative vector function. It also lets you reparameterize your surface there, your 4D surface that you have. So here, tell me explicitly what we should get. What should we have?
1 plus 2.
Parentheses, okay, I like that. Then what?
1 plus 2t.
Then what?
Root 6.
Then what?
Root 6.
Aha.
Oh, that's right, yeah.
Did you forget the root 6? Happens a lot. It's all the time. Just like the Jacobian, like, oh, I forgot the Jacobian. Gosh darn it. Yeah. Yeah, it happens a lot. Do you know where to go from here?
Yeah.
What would you do?
Distribute.
That's it. Just distribute everything. Pull the root 6 all the way in front of your integral if you can. If you want to try this on your own, what we get for the mass of this curve in 3 space. Super nice. 89 square root 6 over 60. Now, did you guys have a question? Okay. Now, 2 other things start happening. The first other thing. Sometimes we don't get integrals with respect to ds. Instead, we get these integrals with a dx, a dy, and maybe even a dz in there. You go, what? That looks crazy hard. It's not crazy hard. It's not hard, provided you have a parametric equation, and you know how to do it. Provided you have that, all it really is the dr dt, that dr that's split up into dx, dy, dz. That's all that's happening. This is not harder. It's just different. It's going to look a little funky to you at first. Does that make sense? I'll show you exactly how to deal with it. The second thing that can happen, your curve must be connected and it must be smooth. most important, it must be smooth. Disconnected, you just do two integrals. But not smooth, you also have to do two integrals. So you can't have like a cusp. Remember that word cusp, a start point? You can't have that on your curve either. C must be smooth. So if you're given two, listen, I'm not going to write everything down, okay? If you're given two pieces, this means two curves. This means two integrals. This means the mass is the sum of those two integrals. Even if it's a sharp point and they are connected, you still have those two curves, two integrals, and the mass is the sum of those two integrals. Does that make sense to you? So you might, if you have two pieces, you split this up, and the mass becomes the sum. Just do the two integrals and add the results. It's pretty much what it comes down to. It's just, it can get a little funky because you have a lot of organization that's going to have to take place. I want to do one of these problems with you right now. We're going to get a kind of two birds with one stone. We're going to look at something that looks like this and something that has two pieces and go all the way through. Is it super hard? No, it's not super hard. You just got to be organized and know what you're doing. Are you guys following what I'm talking about? So let's do this one, and then we should be about done for today. Kind of looks intimidating, doesn't it? Because it looks so different. Yeah, that looks really funky. What in the world do we do with the dx? What in the world do we do with the dy? And now we got two segments. It can look intimidating. So start small. Start small. Let's focus just on the first segment. Notice this is broken into two segments. So even though they're connected, it's not smooth. It's a segment and then a segment. Are you guys with me on that one? Also, when this happens, listen very carefully. If there ain't no ds, the order matters for your segments. It very much matters. You don't get to pick and choose where you start. This will be your starting spot. This will be your ending spot. So if ever you're confused, like, I don't know what, just pick the first one to be your t equals 0. They're segments. Pick the second one to be your t equals 1. They're segments. And then go from there. I'm going to work quite quickly through this to the point where we figure out what to do with that. So follow along. I'm going to be talking through it, but I think that you guys are able. We've done it 2 times now. So we start with the first curve, this 1 2 to 3 4. We call this the t equals 0 and this the t equals 1. I know that there's only 2 variables, so I've got to be able to define x and I've got to be able to define y. Well, for x, I know I'm going to start at 1, and for y, I know I'm going to start at 2. Well, that means that I have this kt plus kt. If there's another way you want to do it, that's fine. At t equals 1, I now go, well, if t equals 1, my x value is 3, my 1's still there, my t value is 3, which means that I get this k value of 2, and x now equals 1 plus 2t. Can you verify the 1 plus 2t and be okay with that? Are you guys all right with that one? Okay, well, what about y? Y says at t equals 1, my y value is 4. I still have this 2, I still have the k, but my t value is 1. That's why we pick these nice choices. Therefore, my k value here is also 2, and I get y equals 2 plus 2t. This right here is what I use to reparameterize my first curve. Show of hands, you understand that concept. Are you sure? Now you listen carefully right now. Do you see how x is this and y is this? And from here, just rewriting it. From here, I'll be able to create my vector function. Be very straightforward. I'll have 1 plus 2ti plus 2 plus 2tj. And okay, that would be the vector function. Are you still okay with it? Can I have your focus here? Let's if you don't blink on this one. You are going to miss it. You can't miss this. Are you guys okay with finding the reparameterization and using it for your vector function? Here is how you find this and this. It's just like every u sub you've ever done in your life. If you have a substitution for x, then you take a derivative of both sides, you get a substitution for dx as well. Did you see where it came from? If you do a substitution for y, you take a derivative on both sides with respect to t, dy dt, this dt moves over, you get a substitution for dy. Those are the pieces that are going to allow you to take care of the dx and the dy. Kind of neat? Kind of neat. So I'm going to deal with my first integral completely through my first curve, then I'm going to deal with my second one. I don't want to get jacked up. I don't want to make the mistake of losing these two parameterizations for that curve. So I deal with my C1 all the way through, then I start my C2. Does that make sense? You don't go jumping around. It's too easy to make a mistake. So here I go, okay, well, the next step after I find my vector function, I have my x, my y, I've got my dx, my dy, that's an additional step for here. I try to find my first derivative. I find the magnitude of my derivative of my vector function, which is square them, add them, square root them, and we get 2 root 2. Oh, actually, you know what? No, we can make it even easier. Yeah, that's just split up. Oh, that's fantastic. I'm going to save you a big old step. Ready for it? You see any DS? It's built in, right? There. It's built into it. That's fantastic. I'm doing extra work for you. It's built into it. If you notice it when you took the derivative of your vector function, you got the same exact two things right there. You guys see that? That's neat. Oh, I love this stuff. Let's just make our substitution. So for this integral over C1 only, we have, what are the t values? Let's go work quickly. What are they? 0. We would replace x with x. Here's our map. We'd replace y with y. dx. What do you replace dx with?
2dt.
Now there's another part of it. Don't forget this part. Then we have this x plus y and then what do we replace dy with? Come on. Now what do you do with it? What do you do with it? This is one enormous term. This is one enormous term. They both have a dt with it. You can do things like factor that and put it at the end. You can do things like that. So here we get our kind of our nastiness. This whole thing is DT'd, if you will. Now, let's see if you follow it, because I'm not going to set this one up for you. I'm not going to do it for you. I think you guys can do it for you. So this, do you feel confident on finding your own parameterization and then just a derivative?
Yes.
Notice we lost the vector function. It doesn't matter. There's no ds. That's a nice part about this. That's pretty cool. Then we go, okay, we'll just take your reparameterizations, use them for x and y, use them for dx, dy. You're going to get 2 dt's, factor it out, and then when we do this, we get 68 over 3 is what we get. How would you do it? How much time we got? A minute. If you set up your second curve, the second one,
X equals 3 plus t, y equals 4 minus 4t.
3 plus 2, very good. And you said y equals what?
4 minus 4t.
Yeah, beautiful. Here, t equals 0, t equals 1. Here's the 3 and the 4. Plug in the t equals 1. You find your case, your dx. Help me out with this. What's your dx?
1. Or dt.
What's your dy?
Negative 4. Negative 1 4 dt.
Negative 4. Just negative 4 dt. So when you plug this in, we get for C2 x, y, just dt for the dx. dx is just that. X plus y, negative 4 dt for the nature of the dy. Factor your dt's like we did before. This ends up being negative 46 over 3. Can you get negatives? Yes. Yes, you can, because of the order of your endpoints. You reverse them, you get a positive. If you add these together, your total answer, 22/3. That's the idea. Do line integrals make sense to you? Okay. Okay, so welcome back. Couple examples here. One really quick one about how to just compute some line integrals. Then we're going to talk about a really important concept. This concept is practically the rest of the next 3 sections. How we accomplish doing line integrals through vector fields. So we're going to spend most of our time in the next section on that concept. This is like a transition area that we have right now. So to get our brains kind of wrapped around it, let's do one more line integral about this line integral, where our curve is represented by a vector function. Now, I want you to think about something. We had this on our very last example, last time in class. If you don't have a ds, look at your integral. Do you have a ds? Look at your integral. Do you have a ds? No. The only reason why we needed the vector function, the only reason why we needed that was so that we took a derivative of it and then took the magnitude and used that to replace the ds. Do you remember that? Well, in the last example, when we didn't have a ds, even if you have a vector function, we don't need to take the derivative and find the magnitude unless we have the ds. Nod your head that you understand that. The derivative and the magnitude of that's what lets us substitute for the ds. If you have this line integral where it's like a dx, a dy, a dz, think about it as the ds is kind of separated throughout that. Okay, we don't need one substitution for the ds. We get to take a piece by piece derivative instead of the derivative and the magnitude. Now, okay, so what do you need the vector function for? Well, I told you something. No matter what you do on any of these line integrals, you have to have an x, a y, and a z. So I've done a couple things. We found ways to find the x, y, and z explicitly and then find a vector function from it. I've given you a vector function and we find x, y, and z from that thing. So in this case, let's look at the board right now. So what you're doing, look. If there's no ds, there ain't no reason to take a derivative of that because I don't have to substitute in the ds for the magnitude of the derivative of the vector function dt. Does that make sense? What I do need the vector function for is, and what I told you to do every single time if you're given a vector function is what? If If I give you a vector function, and I say, I need you to find out some x's, y's, and z's, can you do it? What's the x? What's the x from that? I feel like I've lost you somewhere along the way here, because I got a whole lot of that. No matter what, when we did line integrals from before across segments, we had to reparameterize. You had to have something for x, you had to have something for y, and you had to have something for z, if you have a z. We have to have that no matter what. Now, sometimes if you have a ds, you need to start working with that vector function to take the derivative and find the magnitude to substitute for the ds. We have to have that. If we don't have the ds, there's no derivative, there's no magnitude, but we still have to find x, y, and z. So no matter what do you have to find? X, y, and z. Can you do it from a vector function?
Yeah.
Can you do, well, let's find out. What is your, from here, what is your x component? What's your x component? Then you found your x. What is your y component, please? Do we have a z component?
Yes.
Come on, people, help me out here. Focus on this for today, for right now, okay? Do we have a z component?
Yes.
What is it?
2.
Now, we also learned something else from the last example that we did in class. It was, yeah, you might not have a ds, but you do have some derivatives up here you're going to have to substitute for. In fact, instead of a ds, think about it this way. The ds, that arc length, it encompassed this whole derivative, where we found the derivative and we took the magnitude. If you have a dx, a dy, and a dz, you still practically have that idea of the derivative of the whole vector function, but it's broken up, which means instead of taking the derivative of the whole thing and substituting for ds, I can take the derivative of each little part and substitute for dx and dy and dz. Does that make sense? So it's two concepts that we deal with in line integrals. A ds concept, you're taking a derivative of the entire vector function, you're finding a magnitude, and you're substituting. Or a dx, dy, dz. You're taking from the vector function, from reparameterizing a curve, you're finding x, y, and z, and then from right here, hey, look at that. Could you replace all these x, y's, and z's with what I have right here, the reparameterization?
Yes.
Sure. Can you, from right here, tell me what dx would be? Think of like a u sub. Can you do it? Take a derivative of both sides. Dx would be e to the t dt. You've taken the derivative of x with respect to t, and that's where that dt is going to come from. Does that make sense? Are you sure? Let's keep on going. If we find dy would be what, please? Negative. Perfect. And then dz, come on. Don't forget the chain rule. What is it? 4. So that was basically the whole idea for line integrals. It's find a curve somehow. We're given a curve here. Find x, y, and z, no matter what. If you find it from the curve, great. If you have to reparameterize it, that's okay too. If you have to have a vector function, when's the only time you absolutely have to have a vector function? When you have dx, dy, dz, or when you have ds?
Dx, dy, dz.
The dx, dy, dz is for when you have x, y, and z somehow. You absolutely have to have a vector function if you have a ds, because you take a derivative of it and then the magnitude of it, and that would replace the ds. Does that make sense? So you get this, you need this. Because from this you can take a derivative and a magnitude and it replaces that. Make sense? If you don't have this, you just need x, y, and z. You can get it from a vector function, but it's kind of extra. You don't need it because it's built in. Now let's go ahead and let's replace this stuff. Again, we're moving kind of quick today. What we learned also was that, hey, if I'm reparameterizing all of this junk in terms of what variable, what's my new variable? What am I going to have?
T.
Then the t is all that really matters. So the t gives the bounds of integration. So I'm going to do it kind of quickly. We're replacing x with this, y with this, z's if we have them with this, and then we have dx, dy, dz. So it's just a huge substitution. In our case, we'll have e to the t plus e to the negative t, but then our dx is e to the t dt. Plus, then we're going to have x times y, e to the t times e to the negative t, and our dy, well, that's this. E to the negative t dt. Lots of t's floating around. Plus, then we have the y again, e to the negative t, but then we have the dz. Well, the dz is looks kind of crazy, but I want to see if you can follow it. Do you see where the 0 to 1 comes from? 0 to 1s are the bounds for our parameter there. We have x, y, dx. X, y, y, x, y, dy. And then we have y, dz. That's where all that's coming from. Now, how many dt's do you have? Do you have a dt on every single one of those terms? Let's put it in the back. Factor it out, put it in the back. Also, some math magic's going to happen here. If we distribute on a lot of this stuff, we get some nice things. If we distribute this and factor the dt's, this gives us e to the 2t, this gives us just 1. Do you see it? This is just 1 multiplied by that. This is going to give us 4e to the t. So our integral looks something like this. When it's all said and done, which one actually looks nicer? That one? Or that one? This one. Because it's got a lot of different variables. And it's split up the ds. That's why we don't need to do the derivative then. It's split up the ds. We just need dx, dy, dz. Notice how dx, dy, dz coming together would create kind of this ds concept where it's a derivative vector function. We just have it separated. So as long as we can re-parameterize this, go from the bounds of our parameter, it becomes pretty nice. Could you integrate this if I had you do this on your own? That's kind of basic, just some trivial u subs, if that. If you want to check your answer on this, looks kind of funky, but this is the answer. Just like that. Now I want to switch gears a little bit. We right now, I've given you a lot of examples, and I've tried to give you an example of basically everything you're going to be asked for line integrals. Stuff on segments, stuff on curves, stuff on vector functions, getting x, y, and z from vector functions, creating vector functions from x, y, z, doing things where you don't even need a vector function, but then maybe getting x, y, z from it. We have lots of examples. The next thing we're going to do is this. We're going to tie the idea of, if you haven't noticed this, we haven't really talked about vector fields yet. We're going to talk about, what if you have a line integral and this thing's going through a vector field? What's that even mean? That's the focus for the next few sections that we're going to do, and we start it right now. So let's talk about line integrals through a vector field. We're going to call that f. So for this, a vector field, where we can re-parameterize it in terms of t, just like we did. So for a vector field, and some curve given to us by a vector function. You guys get the idea? We're going to have this curve. So you guys remember vector fields, all those arrows going all over the place in the 3D, and we say, okay, well now let's take this curve, a three-dimensional curve going through a vector field. What is it doing? What's it look like, and what do we get out of it? Well, what it looks like first. If we want to find the line integral along the curve through a vector field f, it's given to us by this. It's going to be given to us by the vector field, re-parameterized in terms of t. Dotted with. That's a dot product. Dot. The first derivative of the vector function that's giving us the curve dt. you're going to see a lot of similarities. First, I want you to see something. Do you see how the derivative is like built into your line integral like every single time? You got a dx, dy, dz, or you got a ds, which encompasses the derivative of this thing. Look, we have the derivative again. Now, listen carefully, because a lot of people make this mistake. For your typical line integral, not through a vector field, you take the magnitude of the derivative of your vector function if you have a ds. Do you guys remember doing that? You find the magnitude a lot. Is that a magnitude? Look, is this a magnitude? It can't be. Because a dot product works with two vectors. That's clearly a vector. This needs to be a vector. You find the magnitude, you now have a scalar. Dot product won't even work. So you don't have to find the magnitude. That's actually nicer. That's more better. Okay, that's a good thing. You don't want to have to find the magnitude because a dot product won't even work. And now that you understand that. It's still got that derivative though. So if you want to think about it this way, this is pretty close to the ds concept. Also, hey, what's the variable that we're going to have a lot of in here? What's the variable? Just like this, you're going to reparameterize it, which means that our bounds of integration are also going to be in t. Are you clear on that? Are you clear on what that, well, you're not clear on how to do it. What I'm asking is, does the formula make sense for you? Do you see where the pieces are? This is the formula for what, people? What is it? Formula for the vector field. This is the formula for the derivative of the formula for the vector function, or the curve. You're going to see this a lot. I'm going to make it make a lot more sense when we talk about Green's theorem, when we start talking, line integrals across conservative vector fields, and when we start talking about Green's theorem and things like that. This is written like this. There's some shorthand for it. Looks like that. Looks like that. I want to see if you can see that this is the same thing. Check this out. dr, hey, look, dr would be the derivative of r with respect to t. It's this. That's all it is. F literally is f. It's just I'm showing you here that you're going to have to reparameterize it. Does that make sense? So I'm kind of showing you more explicitly here. This means the same thing. Now, what is it that we're doing? Well, this is a crazy concept. What this represents, what this is, so taking this curve and moving it through a vector field. A vector field represents a whole lot of little arrows, right? Those little arrows can represent, focus please. Listen, some of you guys are zoning, I can see it in your eyes. If I move a curve through something that has a whole lot of arrows, forces, things with magnitude, I'm having to work against those forces to move something. Work against those forces. What this represents is work done by moving a particle along that curve through a force field. First time I heard it, I was like, force field? Yes, finally Star Wars. Finally, I get to learn how Star Wars works. I'm going to make a lightsaber. It'll be freaking awesome. Unfortunately, that's not what this means. That's why I became a math major, man. But no, what a force field is a vector field that represents forces. Much to my chagrin. This represents work. That's what it is. So when you hear this and I say, hey, what's a line integral through a vector field? What does it represent? What's it represent? Work. That's what you're doing. You're doing work. I know it's work, okay? But that's what it represents. What it represents is moving a particle, something, okay, just something, along a curve through a force field, a vector field that represents forces. So what you're doing when doing line integrals through vector fields is work. Is work important for you physicsy engineering people to know about?
Yes.
That's how we do this stuff. So this represents work done by moving a particle along a curve through a force field. It's a vector field that represents forces. That's what that means. Now, we just have a couple of examples to illustrate this concept. The first one I want to talk about, well, actually, it doesn't make sense. If we want to do a little recap, we're making a transition. Look at the board over here. This right here, this ain't no vector. Okay, this is not a vector field. This is just a function. That's what that is. This is a line integral talking about, okay, well, that is my curve, and then we're overlaying that onto some sort of surface and finding an area between the curve on the surface and that curve on the XY plane, or XYZ surface, if you will. That's what we're doing here. We can do it, but we're finding the area between a couple curves, basically, is what we're doing. It doesn't understand that. This is different. This was not through a force field or a vector field. This one is now. We're going to have a little different concept. Is it hard? Not really. All you need to know is how to take a derivative, how to plug it, how to reparameterize, which you're going to be given this curve. So given a curve, take a derivative, reparameterize, and do a dot product. Can you take derivatives? Can you plug in t's for x's, y's, and z's? Like, it just showed me you could do. Can you do that? Now it's just a dot product, because instead of just having a function you can plug crap into, you have a vector that you can plug stuff into, and then you got to take a dot product to get rid of that vector concept. Make sense? And it's going to give us a scalar. This whole thing works out to a scalar, because work, you got to quantify that. So when we say this represents work, you're going to end up with a number, just like we end up over there. So let's do, man, maybe 3 if we have time for it. I doubt it. Okay, there we go. Kind of a simple one. We'll do a 3D one here in just a little bit. So we're going to find the work done by moving a particle along that parabola from that point to that point through the vector field. That vector field. Are you guys okay with the concept? So what are we finding? Work. How are we going to find it? Well, we need a couple things. Firstly, have I given you a curve? What's the curve?
Oh.
It's a parabola. But just like before, you now have to have the vector function, because you're going to have to take a derivative of that. Does that make sense? You can't just take a derivative of this. It's not in the correct variables. We're going to have to reparameterize that. You have to do it. Now, I've shown you that several times. From thinking back to last time, how to do it with segments. Remember talking about segments? No? We're talking about segments, how you do the x equals c plus kt, y equals c plus kt, and you plug in the first point for x and y and z if you have it. That's pretty easy. If you don't have segments, use the trivial reparameterization. Like, what's that mean? Well, I'm going to show you right now. So, for your curve, if you don't have segments, for non-segments, please try a trivial parametric equation or reparameterization. Do a trivial parametric equation. What's trivial mean? Here's what trivial means. A trivial reparameterization or parametric equation. You call the dependent variable in this curve, you just call it t, and then y automatically gets reparameterized in terms of t. For instance, what's the independent variable in this? If y depends on x, what's the independent variable? Call x t. Call the thing, the variable that you would plug numbers into naturally, call that thing t. Now, if you replace x with t, do you see how it automatically takes care of the y for you? Yes or no?
Yes.
So if we call x t, then y would be what? Please, come on.
T squared.
Perfect. Yeah, that's exactly right. That's called the trivial parametric equation. What it does, it just takes your independent variable, it calls it t, and that automatically takes care of your dependent variable for that curve. Show of hands if you feel all right with that one. Now, that's trivial. Now, here's what you want to happen. I'm going to show you what you want to happen, then I'll show you what's going to happen here. Here's what you want to happen. What you want to happen is to have t equals 0 give you this point, and t equals 1 gives you this point. That's what you want. Remember that from our segments? It was really nice, and we made them that way. But here, if I plug in 0 for t, is it going to give me negative 1? No. And if I plug in 1 for t, it's not going to give me 2. So that's what you want to happen. If it doesn't happen, here's a nice little thing to do. Now look at me. Now look at the board. Now look at me. Now look back at the board. Now do some jumpy jacks. No? You guys need to wake it up out there. Goodness gracious. You guys look like you're just dying. You alive? Okay. If that doesn't happen, if you can't just plug in 0 and get this and 1 and get that, if that's not working, here's what to do. Notice something. These points, in order for me to move along this curve, these points have to be on this curve. Do you guys get that? I can't be like, hey, move from negative 1, 1 to 417, because 417 isn't even on the curve. I've got to be on the parabola, which means this. If I've used a trivial parameterization, then I can call t equals this number and t equals this number, and it will have to work out for my parameterization. For instance, if I call t equals negative 1, then y would equal 1. If I call t equals 2, then y would also equal 4. X would equal negative 1 for t equals negative 1, and x would equal 2 for t equals 2. So if you've used a trivial parameterization, then your t, just look at the board. If I've made this, do you guys understand this is trivial? I'm just calling, t is a dummy variable, it's just our parameter here. If I just let x equal t, and I go to my x values, those now are my starting and stopping t values. If x equals t, and x equals this, then t equals this, in that order. Does that make sense? That's a really nice way to do it. So if you can't just plug in 0 and 1 and get the points that you want, use a trivial parametric equation where your independent variable becomes t. It lets you reparameterize this whole function for your dependent variable, and just look at what you called your t. If x is t, then t is negative 1 to 2, because x is going from negative 1 to 2. And look what happens. If I plug in negative 1, I get 1. If I plug in 2, I get 4. It's moving us to that point. Head nod if you're okay with that one. That's nice. Now, we need two things. We need two things for this to work. There's only two things. It's really easy to do. Just don't lose it. Here's what you do. We need to find the vector function, or the vector field, the function for the vector field. And it's got to be in terms of t. And we also need the curve. We need r. Those are the two things that we need. So let's see. Let's see here. Hey, have I given you a curve? Have I given you a curve?
Yeah.
From that curve, this one, right there, were you able to redefine, listen carefully to my words, okay? Were you able to redefine x as a t variable and y as a t variable? That's going to give you this. Have I also given you a vector field? Have I given you that?
Yes.
Come on, help me out. I need more than what I'm getting from you. What have I? Don't just say yes. What is the vector field? What's it say exactly? What's the big F? What is it? Do you see it up there? It says B, big F, and then an X with a Y. Yeah.
Yeah.
Read it.
X equals Y.
There's an I,
Yeah.
and then a
J. Y.
bunch of junk in X and Y with a J. Now, do you have anything that lets you change X's and Y's into T's? Do you have anything that lets you do that?
Yes.
Yeah, let's change that. So from this, if you've already defined x and you've already redefined y, then we can start redefining this. So we change our f and we get, well, what do you tell me? What's x going to become? Come on, quickly. What's x going to become? I need more than nothing. What's x going to become?
T2.
E2, then do it carefully. What's that going to become? Perfect. Am I still going to have an I? You have to for the dot product to work. Plus, okay, what's the y going to become, please? What's the y? Come on, quickly. Perfect. How about this? Vector function, curves. Curves, vector functions always work this way. It's the x component I plus the y component j. Which means whatever you have picked over here, can you still use this over here? It's used twice. It's used twice. You use your x and your y to redefine your vector field. Use your x and y again to create your vector function. Can you please tell me what is left side only? I haven't got much out of you guys. If this is xi plus yj, and I know what my x and my y are, can you please redefine this, reparameterize it, let me know what this is going to be, please? Perfect. Let's take about a 15-second recap. Make sure that we're going through this okay, all right? There's a difference between basic line integrals and line integrals through vector fields. You must have these things all the time for your line integrals through vector fields. You have to have a vector field and you got to have a curve. The vector field, we're always trying to redefine this in terms of t, which means that if I give you a curve, you use that curve for two things. Number one, you use that curve to redefine x and y in terms of t. I've given you a way to do that. Trivial substitution right here, that x equals t and then y has to equal t squared because, well, it's x squared. Use this twice. And it's very, very easy to do. Use it twice. One, man, hey, vector functions are literally just xi plus yj. And then plus zk if we have that. We just get that. And now if you're okay with creating that, we've done it a couple times now. The vector field also needs to be redefined. But once you've done this, it's just a matter of substituting it in there. That's in terms of t. That's in terms of t. That's really all we need. Should fans feel all right with that one? Was this too tricky? You guys okay with where the t comes from? If it's a trivial substitution, then these two numbers, your x numbers, your independent variable numbers, become your bounds for t. That's all that's happening. Now let's keep on going. So let's look over here. What's the next thing you might want to do before you set up your integral? What would you do now? Look right here. We have our f. Do we have this piece? Come on, everybody in class. How do you find that piece? Derivative. Let's do a derivative. If we do, this should be kind of an easy part. What's the derivative? Oh, hey, by the way, with respect to t, that's why we have that. These things are the same thing. Tell me what it is, please. Beautiful. Do I need to take a derivative of this? Okay, so we've done this. We've got our vector function. We have our vector field. We took the derivative of our vector function. Come on now, what's the next thing that we would do? Dots. Let's dot them. So right now I want to find f dr, which basically means take f, dot it with whatever you just found. That's all I need from you. So we've redefined our vector field, we got it. We've made up a vector function based on that curve. It is the curve, and we've taken a derivative of it. Now if we dot them, it looks like this. True or false? Dot product will work out just fine for us. What do you think? Do we have two vectors? True or false? Dot product will work out just fine for us. True or false? It's going to give us a vector when I do the dot product. No, it'll give me a scalar function. In fact, a scalar function is really easy to take an integral of. That's really cool. So let's do it. Do you remember how to do dot products? I'm praying that you do. What do you multiply?
The components.
Just multiply them and add them. That's a component for component. So here we get that this is, well, the I components is 1 times this, plus the J components being multiplied. That's it. This piece right here is F dot dr. That's it. That's the only thing that I need you to do is take, well, and there's a dt hidden back there. We didn't write it, but there's a dt that it's tacked on to this whole thing. If you want to write the dt and kind of be pedantic about it, but it's not really pedantic, you need the dt at the end of it. What I want you to do is understand that all we've done basically is fix the inside of my integral. Does that make sense? You can see it right here. This piece is this piece. That's what we have. So let's rewrite it. So from here, I know that work done is going to be an integral. It's going to be an integral from the bounds of t that you just created. What are the bounds of t we just created? Come on, quickly. It's going to be, well, the vector field dotted with the derivative of the vector function we get from our curve. That's right here. So that's the inside piece. All we have is this t e to the t squared plus 2t cubed dt. The dt's here. This notation could be written just right at f, or sorry, r prime. And then that's right there. Can you do that? Can you do that integral? I'm not asking you to do it right now, but can you do it if I asked you to do it?
Yes.
How would you do that piece? This piece? Basic. Plug in some numbers. That's all there is to it. It looks a little bit funky, the answers on some of these. After finding a common denominator, you get that. Hey, would you like to try one more just to make sure that we can do it?
Yeah.
You're like, no. We're going to do it anyway. So we got like an hour. So, well, no, less than that. 45 minutes. So we do one more. Did this one make sense to you? Is this out of your reach, do you think? I think you can all do it. It's literally just redefine, plug in x for some t's and y with some t's and z with some t's, take a derivative and dot product. So let's do one more. Are there any questions at all? Because I really am going to erase a lot of stuff on this side. Anything at all? Okay. Okay, so we're going to answer the same question. We're going to find work. I'm going to give you a vector field here. And you're going to get some practice right now on reparameterizing segments, because a lot of you just said, I forgot how to do that completely. So let's say I got my curve, and my curve says, I want to go from this to this. Is the order of the endpoints important?
Yeah.
Absolutely yes. Yes, there's no DS here at all. The order of the endpoints are very, very important. You don't just get to switch a root, okay? You got to keep the first one, the second one, the second one. Does that make sense to you? Okay, so let's go through this thing. The whole idea is we need two pieces. All we really got to do is reparameterize our vector field. But we got to have t's to do that. And we need a curve, but we got to have t's to do that. Now, I showed you something last time. I'm hoping it stuck with you. If ever you have a segment, if ever you have a segment from one point to another, which is what we have here, if we have a segment there, do you remember what to do at all?
Find the vector.
What values of t do I want for segments? Do you remember that?
0 and
I
1.
always want 0 and 1. Which one of these would you call t equals 0? Which one would you call that? So let's call this the point when we have t equals 0, and let's call this, oops. Let's call that the point where we want t equals 1. Listen. For segments, this always works. You can always do this for segments. Can you do it here? No, you can't. It's not going to give you the proper points. But for here, you can always let your parameter equal 0 for the first point and 1 for the second point for segments, pieces of lines, because the parameterization is really nice. Head down that you understand what I'm talking about. Now, how this, well, okay. How many letters do we got to reparameterize? 2 or 3?
3.
We got x's, y's, and z's. If you want the shortcut, and I know a lot of you guys love shortcuts, here's the shortcut to do it. Here's how to do this as fast as humanly possible, all right? Without just doing it all in your head. If you're, now listen, you do have to know this even to have been successful in this class at this point. All of these lines are all written in terms of some constant plus kt. Do you remember that from our basic parametric equation for lines? Tell you what, if your t equals 0 for all three of these, then this, and this have to be your constant, which means that you put your x, your y, and your z, and your constant is going to be -1, 3, and 2. Just go right down the line, put your x, put your y, put your z, they have to match up. Does that make sense? Now, as far as the k goes, I don't know yet. But that's why we have this other point. So let's think about this. If I let t equal 1, what's the, hey, come on, help me out. What's the x value when t equals 1? What's the x value? Everybody, what's the y value when t equals 1?
-2.
Well, what that means is that if t equals 1, this is why you want zeros and ones. Zeros because it gives you these values. Ones because the t is basically gone. You just have k. It's easy to solve for. So if I let t equals 1, basically you don't even look at this. You just look at the k's. If t equals 1, x is now 1. Does that make sense? If I solve for the k, I just add 1. That means that k equals 2, and we get x equals -1 plus 2t. Try that technique with me. Try it. If t equals 1, this is basically just k. If t equals 1, the y value is -2. I would have to subtract 3. What's -2 minus 3? Yeah, then that means that y equals 3 still, yes, minus 5t. Are you guys getting the picture here? This is the fastest way to reparameterize that I know, at least. Let's talk about the z. If t equals 1, we just have a k. If t equals 1, the z is 4. I would take 4, subtract the 2. My k would have to be 2. 2 plus 2t. Yeah? Yes, no? You guys feel okay with it? Now, two things have to happen. You use this twice. You use it once. Hey, look. Are all x's, y's, and z's in terms of t? Hello?
Yes.
Could I take these and plug it in here? Is it going to look really, really nasty?
Yeah.
Yeah. Can you, and here's an important part because people get kind of jacked up on this. Can you take this and create a curve from it? A vector function from it? Remember that vector functions are just xi plus yj plus zk. Let's do both. I'm going to start with the vector function. So if I do, need some room for this one. Remember that this is x, y, and z. Well, all I need to do is take this, x component I, take this, y component j, take this, z component k. That's always how we find our vector functions. If you've already redefined x, y, and z, you literally have your vector function right there. We got x, y, and z from our vector function before, now we're just creating a vector function from our x, y, and z. Seems logical. Should be able to go both ways on that thing. Head down if you're all right with that one. Left side, right side, are you guys okay with it? Now, I'm going to write it down, but can you tell me what this would be if I re-parameterize? I have to do it right here. If I re-parameterize my vector field in terms of x, y, and z, say it loudly so I can actually hear you here, but tell me what this would all look like, please.
-1 plus 2, 2. Plus 2 times 3 minus 9, 2.
Somebody else, keep it up. What am I missing?
Plus 2.
Before that. I. That's the I. Kind of nasty, but that's the I. Then I go, okay, plus. Plus, somebody else, come on, help me. I know you guys can see where this is coming from. What else do I need? Plug in what? Okay, you can distribute right now if you want to. You don't have to. And then there's a J. And somebody else, let's go to the right side. What's the next part of it? Plus what?
-1 plus 2t.
Good?
Minus 3 minus 9t.
Gotta have parentheses, gotta have double parentheses, gotta have a K component. Let's follow this along. Can you guys see how to get x, y, and z and make a vector function from it? Do you see where that's coming from? Hello, yes, no. Can you take the x, y, and z, and even if they're really nasty, plug it into a vector field, and take your vector field and reparameterize it? Can you do that? What's the next two things that you would do? Something's got to happen here because it's freaking nasty. What would you do there? You'd have to simplify that. So simplify that. I've done it for you. What it ends up looking like is this. So that's the simplified vector field as reparameterized in terms of t, right there. We also do one more thing. Bless you. What would you do with, would you take a derivative of this, like ever? Do you ever do that? Do you take a derivative of this guy? You have to do that. So the derivative here is, well, it looks like it's 2i minus 5j plus 2k. Can you guys follow me on the derivative of that one? That's pretty, I love segments and lines because the derivatives are really, really nice. So that's the derivative. Do you have to find the magnitude for this? Come on, listen up. If this wasn't through a vector field, would you have to find the magnitude of that?
Yes.
Yes, if you had a ds, you'd have to substitute for that. Here, vector field, we don't have to do that. What do we have to do? Come on, what do we have to do? We got to do a dot product on this. So if we dot these things, we have this whole thing. Dotted with this thing. Tell me something. Do you feel confident that you could perform that dot product? Is it going to give you a vector? Is it going to give you a scalar? What's it going to give you? I'm going to dot product for you. I'm also going to combine some like terms. You should be doing this on your own. When I did this on my own, what I got out of this whole dot product is negative 18 minus 22t. Now let's wrap it up and be done with this section. Are you done? what should you do? The integral. Okay, let's set the integral up. What's the integral going to represent? Knowing that this is a curve, moving a particle along a curve through a vector field. What's it representing?
Work.
It's going to be work. And that work is going to do, well, it's going to do something. It's going to move a particle from this point to this point along a segment. Now, we've redefined that segment. That's what this is all about. We've redefined the points even. Notice how it'd be really difficult to plug in these numbers on an integral, on a single integral. It'd be like, what am I doing? That's why we reparameterized this. So what are the values I have to go from? And they're all in terms of t. Hey, is the scalar function you end with also in terms of t? Then that's really convenient. That's why this stuff actually works. So t goes from 0 to 1. Whatever you get out of the derivative of your vector function dotted with your vector field as reparameterized in terms of your parameter t. Take an integral dt. This one's just brutally easy. Brutally easy? Is that even a thing? I don't know. It's pretty easy. But when you work all this out, what happens is you get negative 29. Is it possible to get negatives in work? Yes, absolutely. That's the idea. There are some word problems where you create like some force vectors. For instance, if we were talking about like, I think one of the problems is, hey, you're moving around a staircase where your x is a certain parameter in t, and your y is a certain parameter in t, and your z is a certain parameter in t. Could you find a vector function if I gave you x and y and z? Of course you could. Could you find a force if I tell you that this person who weighs 90 kilograms is climbing the staircase? Where's her force being applied? Or his force, I guess 90 is pretty heavy, 90 kilograms. Well, it's being applied directly down. So if I told you this person that weighs 90 kilograms is climbing a staircase, then your force looks like this, negative 90k, because you're applying force vertically. That's how you would get that. So if a person weighs 90 kilograms and they're climbing up, their force is being applied downward, negative 90, and you're just climbing the staircase. You're only moving upward, really. That's how we're calculating this force in this case. How much work is done? You take the vector function where I've given you x, y, and z. You take the force, pretty darn easy, dot product, or do a derivative, dot product, integrate, and you're pretty much done. Does that make sense to y'all? Okay, we're not going to do another example. What's going to happen right now is we're going to take a 30-second break, and I'm going to come back and I'm going to tell you about how you do line integrals if your vector fields are conservative. So listen carefully right now. This is what we do if our vector fields are not conservative. This is it. We've already done it. So when you start asking the question in your head, well, how do you do line integrals across vector fields when they're not conservative? We've already answered that. Now your lives actually get easier. I'm going to show you how to do line integrals across conservative vector fields, and there's some theorems that help us do that. Like, well, you'll see.